So hi everyone, welcome to today's SciML webinar. We're excited to have Bob Carpenter as our speaker and Professor Samuel Livingston as our session chair. I'll go ahead and introduce the session chair for today. So Professor Samuel Livingston is an associate professor in computational statistics at University College London. He works on Markov chain Monte Carlo methods, particularly gradient-based methods such as Hamiltonian Monte Carlo, but is also more broadly interested in Bayesian modeling and computation. He currently holds a New Investigator Award from the Engineering and Physical Sciences Research Council in the UK. And in 2021, he was awarded the Blackwell-Rosenbluth Award from the International Society for Bayesian Analysis for contributions towards Markov chain Monte Carlo theory and methodology. With that, I'll pass it on to you. So.
Okay, thanks very much, Keith. So it's my pleasure to chair the seminar today. So without further ado, let me introduce the speaker. So this is Bob Carpenter, who's a research scientist at Flatiron Institute, where he works on probabilistic programming languages, automatic differentiation, computational Bayesian inference, and applied statistics. He designed the STAN probabilistic programming language and is one of the STAN core developers. Bob has a PhD in cognitive and computer science at the University of Edinburgh and an undergrad degree in math at Michigan State. He spent 25 years studying natural language. He was a professor of computational linguistics at Carnegie Mellon and an industrial researcher and programmer in speech recognition and natural language processing at various places, Bell Labs, SpeechWorks, and LingPipe. And today he's going to talk to us about Hamiltonian Monte Carlo. So over to you, Bob.
Great. So can everybody see the screen there?
Yeah. It's not yet full screen, but
yeah. Let me work on that. Okay. So is the sound okay here?
Sounds good to me.
Okay, so what I'm going to be talking to you about today is multiscale MCMC sampling, and we're going to be using delayed rejection and generalized HMC, combining a couple of standard techniques here. I'm going to try to say what all of these things are and sort of walk through what I think is a fairly logical sequence of steps that got us to where we're at today. And this work, just to frame it, I think is probably where we're going to be going next with Stan in terms of implementation. And it's definitely where we're putting all of our research in MCMC now. Well, maybe not all of it, most of it. So what is the problem? We want to do Bayesian inference for multiscale posteriors. And what do I mean by multiscale? I basically mean that the spectrum of eigenvalues of the Hessian, that is the second derivative matrix of the log posterior density, that varies with the parameters. So when you change the parameters, the curvature changes. We're just measuring the curvature based on the second derivatives, right? The problem we're facing is that zero order and first order methods like Gibbs or HMC and even just fail. They can't handle these multi-scale distributions. Gibbs can in some cases if everything's nicely axis aligned. Second order Riemannian HMC winds up being just way too expensive at high dimensions. It can adjust for the second order curvature, but it's super expensive and unstable to actually implement. So nobody's kind of cracked that. As an aside, I really think some kind of like low rank plus diagonal Riemannian HMC is something we're going to be looking at next, because we'd really like to be able to not just adapt our step size, but actually do something that's computationally feasible to do local preconditioning or adaptation to curvature. So the solution that we're going to provide here, though, for this is to provide a multiscale integrator. This actually spun out of my job talk at Flatiron when Leslie Greengard, who's one of the world's best-known PDE solvers, asked me, why in the world doesn't HMC use variable step sizes? And I said, well, we don't really know how to handle detailed balance for it. And then I went to figure out how we could do that. And it turns out other people had solved that problem before me, and we just had to apply it, right? So what are we trying to actually calculate here? Well, we're trying to calculate quantities of interest for Bayesian inference, right? We're going to start with this posterior P of theta given y, and I'm just laying this out to settle some notation, right? And that's going to be proportional to the likelihood of y given theta times the prior of theta, right? So y's data parameters are theta, right? We care about estimating this posterior, but mainly we care about these three different expectations that I wrote down. In Bayes, typically when we estimate parameters, we take posterior means or expectations. When we calculate event probabilities, that's the expectation of an indicator function. When we want to do posterior predictive inference for new data, that's again a posterior predictive integral. It's just an expectation of that prediction given theta, right, conditioned on the data y. So all of the things we're actually interested in computing are expectations. And what we're going to do is we're going to use the Monte Carlo method. The reason we named Stan is because Stanislaw Ulam was one of the original developers with Fermi of the Monte Carlo method. And the idea is, let's say we have a density, a posterior density p theta given y. What we're going to do is and again, I'm just sort of settling notation. Hopefully everybody knows all of this. We're going to take a sample of draws, theta 1 through theta m, from our posterior, and then we're just going to evaluate our posteriors by plugging in, right? We just take an average of our posterior draws. That's going to be exact in the limit of infinitely many draws, and it's going to be approximate with finitely many draws. But when people talk about Monte Carlo methods being approximate, they're not approximate like variational methods in that in the limit they get the wrong answer. They're approximate in the sense that they typically only give you 1 or 2 decimal places of accuracy, not that they give you bias. The one case where they do tend to give you bias is in these multi-scale distributions, which is why we're tackling this problem. So fast forward a few years, Metropolis et al., which was contentious, so I don't want to get into the history, developed the MCMC method, because usually it's impossible to draw an independent sample, right? So instead, we set up a Markov chain where the stationary distribution of that chain is the target distribution. This turns out to be relatively easy using the Metropolis method, as we'll see. And we use the same plug-in estimator once we get these correlated draws out of, or anti-correlated draws out of MCMC, right? And what we're interested in is we're interested in controlling our standard error in our estimates. Remember, we're estimating these expectations, right? We want to get accurate estimates of those expectations, right? The MCMC central limit theorem, which is preconditioned on everything mixing properly, and we're truly sampling, right, tells us the standard error is going to be the posterior standard deviation divided by the square root of the effective sample size, where the effective sample size is the number of independent draws that would give you the same statistical power as the number of draws you got from your Markov chain, right? With HMC, it's kind of interesting. This can exceed the actual sample size, right? Just to, again, set up notation here for curvature, Hessians are just second derivatives. So what we're talking about here is we're talking about second derivatives of the, oh shit, I missed the, missed the log density. There should be a log here. This is log p theta given y. Sorry about that. And then the entries are just the second order partial derivatives, right? To settle some intuitions here, if you're not used to working with these things, if we have a normal distribution and sigma is its positive definite covariance matrix, the Hessian is the negative inverse of that, right? So we can develop some intuitions around that. Similarly, if we have something that's diagonal, then the Hessian is just the inverse of the variances. Right? Okay, so the spectrum of eigenvalues, the way we're going to actually measure curvature is we're going to look at the eigenvalues. The eigenvalues are telling you how much things move along the directions of the eigenvalues. So essentially what it's telling you is we create an orthogonal basis for the movement, and the eigenvalues are constraining how far you move, right? Basically, it's this decomposition of a matrix into an orthonormal matrix Q and some positive values, lambda, if the matrix is positive definite. If it's not positive definite, you might wind up with negative eigenvalues. You wind up with non-concave situation. So it's going to be positive definite. The matrix is going to be positive definite if all the eigenvalues are positive. And remember, positive definite is the kind of thing we use for covariance. It's the kind of thing that if you multiply it, it gives you positive values, so we can plug it into densities. Density is going to be log concave if its Hessian is positive definite. This can vary. A density can be log concave locally at one point and not at other points, as we find with really complicated things. Again, if we want to think about this in terms of a multivariate normal with a diagonal covariance, the eigenvalues are just the precisions or the inverse variances, right? The nice thing is eigenvalues are rotation invariant. So if you want to think about this, you just rotate. If you've got something like a multivariate normal and you want to figure out what the eigenvalues are, you can just rotate that covariance matrix back to where it's axis aligned and use this relation, That's essentially what the algorithms do, right? The condition number, right? I was just leading up so I could talk about condition numbers. We've got all these eigenvalues, right? The condition number is the max eigenvalue divided by the min eigenvalue. And the reason we're interested in this is those tell us the scales that we need to move on in different directions. And the idea is that if we want to move a unit, that is, we want to move on all the different dimensions, a unit in whatever the natural metric is, then what we need to do is we can't take steps that are going to not work if they're too large. So our steps are constrained by the minimum eigenvalue, and the number of steps we need to take to explore the largest situation is the maximum value, right? So the situation we're dealing with, so the problem is when there's high correlation, the condition can get very bad, right? If this is just static and there's not varying curvature, we can precondition it. So Stan can estimate that covariance and just apply a preconditioner. The problem is when it varies, that is when the Hessian changes at different thetas, and if the scale changes, the spectrum of the eigenvalues changes for different thetas, then it has varying scale. I'm going to show you an example. Varying scales typically require varying step sizes in order for the algorithms to work if you're not doing some other adjustment for curvature. So let's try to make this all concrete with an example, right? So let's talk about Neal's funnel, right? Neal's funnel is a density he introduced in the early aughts when he was writing his slice sampling paper, because this is a really interesting and hard density. The thing about it, though, is it represents a hierarchical Bayesian prior when there's no data, right? And it has parameters x and y. X is actually a vector, and y is a log scale parameter. And the idea is we're just drawing y, the log scale, normal 0, 3, and then we're drawing the values x. So here's our values x along the horizontal axis. We're drawing the values x, we exponentiate and divide by 2. I'm not sure why Radford did that. The statisticians love to divide by 2 all over the place because it puts things on more natural scales in their head. So here what we're doing is we're taking that log scale, turning it back into a scale and sampling these x's. So the problem is when the scale is very low, the hierarchical scale is low, the hierarchical variance is low, all the low-level parameters x are all clustered close together around the origin, right? So we have very high curvature down here when the log curvature is low. We have the low curvature, a very flat region up here where we're in the mouth of the funnel. So this is the mouth of the funnel. This is the neck of the funnel, right? You can see the contours. The other interesting thing about this density is it has no maximum likelihood estimate. As you travel down the neck of the funnel, the density just keeps going up. So if you run an optimizer on this, it'll just run straight down until it runs out of arithmetic precision chasing that pole, right? So this is pretty much the only density I'm going to talk about because it's kind of the poster example for multiple scales. This comes in worse in reality because you're often dealing with multiple parameters, all of which have hierarchical priors. So you're dealing with multiplicative non-identifiability that give you banana distributions, or as one of my colleagues called them, waning moon distributions. So there's all kinds of other things that come in, but they typically show up as either varying curvature or varying scale when they give us problems for something like Hamiltonian Monte Carlo. So this is a good proxy. If you want a good density to try everything at once, if you use a hierarchical IRT 2PL model, that has additive non-identifiability, multiplicative non-identifiability, and funnels in it. So you can try all the sort of difficult canonical cases all at once with that distribution. We use that for some of our harder tests, but I'm not going to talk about that now. Right? So Neal's funnel has highly varying curvature. Right? In fact, what you see over here on the right, so now I've rotated the funnel and I've actually renamed because I took this out of a different presentation. So alphas now are parameters that we were calling x, and betas now are log scale parameter, which we were calling y. Right? And what you can see over here on this plot, this is a log scale y-axis of the condition number. Right? So the thing is, as we go down into the neck of the funnel, this gets very badly conditioned. Right, the amount that you can move up and down is very small compared to the amount you can move left and right, which gives it a bad condition. Here we have exactly the opposite problem. In the mouth of the funnel, we have just as bad a conditioning. If we keep going, the conditioning keeps getting just as bad in the mouth, but it's aligned the other way. Now we have the same scale on the vertical axis, the same sort of scale 3, because it's a normal 0, 3 on the horizontal, but now going vertically, we have a much wider scale, right? So again, the ratio, the condition is bad because the scale along here is much bigger than the scale going horizontally, right? So this is where the scaling problems show up. And in practice, this is very hard. In fact, it's impossible to sample with HMC in any kind of reasonable way, because if you choose a small enough step size to get 3 or 4 standard deviations into the neck, you can't explore the mouth. If you make a large enough step size to explore the mouth, you can't explore the neck. So what happens is you wind up sampling just bands of this. And I'm going to show you examples of that later, of why HMC fails on this. But first, I should say, I tend to just talk in one long drone. Please feel free to interrupt me. Are there questions that I should probably stop? Are there questions at this point?
So there's nothing in the Q&A or the chat at this point, but yeah,
Okay.
I guess we should just emphasize that if anyone wants to ask anything in the Q&A or the chat, we'll pause at appropriate points and let Bob answer the questions.
Right. Please just blurt them out. So again, this is all still sort of by way of background for where we're actually going in this talk, right? So let's talk about the Hamiltonian dynamics. What Hamiltonian Monte Carlo is based on a fictitious physical system where the potential energy is the negative log density. And the kinetic energy, we're going to take a momentum rho, which is going to be the same dimensionality as our parameters. And that's just going to be a quadratic potential, a quadratic kinetic energy, which is equivalently a log standard normal, right? Gives you, when you do this winds up being a quadratic kinetic energy, right? I just put it in probability terms because we're going to be doing sampling with it, right? But if you're used to thinking of physics, this is a standard quadratic kinetic energy like you would get with Newtonian mechanics. Basically, what Hamiltonian did is he took the second order Newtonian differential equations and broke them down into 2 first order differential equations that involved the momentum or velocity and the position. Right? The Hamiltonian is the sum of these 2 things. So we take the position and we take the momentum and we add both the energies, right? The leapfrog step. So what we're going to do is we're going to write an integrator, something that solves this. So Hamiltonian dynamics sets up a differential equation. If I have an initial position and an initial momentum, right? The Hamiltonian dynamics tell you how that position is going to evolve in time. The leapfrog algorithm is a way of implementing that very stably. And what it involves is we take a half step in momentum, a full step in position, and a half step in momentum again, right? And we update the momentum based on the potential. So when we're updating the momentum is applying the potential energy field. When we're updating the position, we're just multiplying by the momentum here. Right. So Hamiltonian Monte Carlo, right, is very simple. What it does is we start with an initial position, we fix a step size, we fix a number of steps, we fit some positive, definite symmetric metric sigma. You can think of that as like a covariance matrix. And we set a sample size M, right? The metric's going to do preconditioning. And then what we do for each iteration, we just resample the momentum. Then we run that leapfrog algorithm to trace out the Hamiltonian dynamics and see how that particle evolves with this new momentum, right? And then we do a Metropolis accept step, right? And our target density is the negative Hamiltonian exponentiated. So remember that the Hamiltonian's the negative log probability. So we negate it, we get the log probability, we exponentiate it, and we get back to the densities that we're dealing with. So we run the algorithm from where we start to a new point, and then we just look at the ratio of the densities in the standard. So this is just standard Metropolis. And we generate a random uniform 0, 1 and test whether that's less than this. And if it is, we set our next state in the Markov chain to our proposal. Otherwise, we set it to the last step. One subtle aspect of this that's going to be important later. I've actually set this up to flip the momentum so that it's consistent with generalized Hamiltonian Monte Carlo. These momentum flips don't matter in this algorithm because what we're going to do every time, we're just going to refresh the momentum on each iteration. It turns out that HMC is really the composition of two stationarity preserving kernels. One is a Gibbs kernel that updates the momentum and always gets accepted. The second kernel is a Metropolis algorithm that is deterministic, right? There's no randomness in it. It just takes the momentum and it takes the position and carves out the Hamiltonian, which makes it a little tricky. And there's some details in our paper about that. But basically that's what's going on, right? In order to make sure that the Metropolis step independently obeys detailed balance, we have to flip the momentum at the end so that it's reversible, right? That means if I take a step and it goes to here, and then I just take a step backwards, I'm going to get back to exactly the same place that I wound up at, right? So this makes sure the algorithm's reversible. When we're done, we just get the samples theta 1 through theta m, right? We did m iterations of this. Each time sample, carve out the trajectory, accept or reject where we're at the end. Okay, so it does a lot of work. It can do in very complicated densities. Sometimes m has to be fairly large, but L, the number of steps, can be anywhere from 2 or 3 with a simple normal distribution up to thousands with really complicated densities that involve nested differential equations and things. So it can get bad. Okay, now we're going
Sure. Maybe there's a good time because there's a question. So maybe this is a good time to ask it. So it's from Kieran Gautier. I'll read it out just for completeness. Okay. So Kieran's asking, I was wondering if you could comment on the use of the condition number to measure the scale of the variance for the parameters in the log of the joint distribution. It seems to work well for the funnel, and at each point, the multivariate normal seems like it can describe that well, but what do you recommend for other things like bananas and things like that?
Okay, so generally what we're doing is just taking the Hessian to represent the curvature. And what you'll see with a banana is that the Hessian is going to be aligned up and down in the top part of the banana, and it's going to be aligned side to side. So the curvature is actually going to change in the banana. Right, the scale doesn't necessarily change in the banana, so you don't necessarily need different step sizes. You don't necessarily need our algorithm to deal with the banana. That one we can handle with standard techniques, although it's still problematic because the Hessian there isn't always positive definite, right, is the problem. So in that case, you can't really look at condition numbers, right, but you can still look at the curvature as represented by the Hessian. Did that answer the question, Kieran? Anyway, ask another one if it didn't. I'm going to go on. But feel free to jump in if other people have questions. Either just jump in and say something or type it into the Q&A. Okay, then we're going to get the sample when we're done. Right, so... Oh, why am I not advancing anymore? Okay, so generalized Hamiltonian Monte Carlo. This is an idea from Horowitz in 1991. So it came very soon after HMC got introduced. Generalized HMC has the insight that we can just partially resample the momentum, right? So in essence, what this is doing, I'll break it down for you without belaboring the math here, is we're taking a weighted average of the momentum we had in the last iteration with a brand new refreshed momentum, right? And this is still exact Gibbs because if rho m-1 was sampled from normal 0 sigma, then we have to bounce back and forth between this 1 minus lambda scaling on the covariance and the square root, the same way we do in Michalewski factor. We're going between variance, which has quadratic units, down to the scale, which has units, right? So there's a square root there. So we know that this multiplication here, this value is distributed with a reduced scale covariance. And then what we're going to do is we're going to complementary do the scale here so that rho's normal 0 sigma, right? So the weighting here balances the variance so that we guarantee that after this update, we preserve the stationary distribution so it's still an exact Gibbs step, right? The reason people thought this might be interesting is it gives us directed momentum. It allows the momentum to carry on across iterations rather than being fully refreshed. The usual use case for this is to take just one step of HMC, which is equivalent to the Mala algorithm, right? But it's going to operate on the position and the momentum. Mala just operates on the position vector. It can get away with that. We're going to take the position and momentum and wind up with a 2 times the dimensionality of the problem, sampling problem, right? But it winds up being equivalent if you do the algebra, right? So the idea is I just do one step of HMC, but I preserve momentum. The problem is this idea is not really going to work, right? It's a cute idea, but it doesn't work as formulated, right? Why does HMC work? HMC scales in dimension by making directed progress every iteration. The Hamiltonian flow keeps us in the region of the high probability. The leapfrog integrator is symplectic, which means it preserves volume, which means the Metropolis accept rate is going to be high. As an aside, the leapfrog is actually a terrible ODE solver. It gives terrible solutions. It's just very good at preserving the Hamiltonian. The problem with GHMC is it's going to revert to a random walk. Instead of making this directed movement, what's going to happen is every time there's a rejection, it's going to flip the momentum, right? And the problem is that's going to send us walking back in the other direction. So we're trying to balance 2 things with GHMC. We want to keep the step size high. We want to keep the momentum refreshed, right? But we want to keep going. In order to keep going in the same direction, we have to move the step size down, right? That's bad because we want to make progress at sort of the nominally acceptable step size, right? So we're kind of in a bind, and this can't be balanced in an effective way as far as I know for this algorithm, right? But it turns out Radford Neal, coming back onto the stage after retirement, fixes this problem along with, this is a beautiful paper, by the way, like all of Radford's paper. This is like an 8 or 9 page paper that just lays everything out so crisply. You wish you could write like Radford, at least I do. So what Radford did, really simple idea, right? Well, in retrospect, these ideas are simple. I don't know how he came up with this. He replaced the IID. So normally in the Metropolis, we do this accept step where we generate this uniform 0, 1, and we compare it to the minimum of the density ratios in 1, right? And we typically take this IID. Each iteration, we refresh this thing, right? So what Radford did is said, well, instead of refreshing it uniformly, instead we're just going to say, take this value, add delta, add a little bit of jitter so that we wind up dealing with ergodicity correctly and get the right thing. And then we subtract or add 2 till we're back inside of 0, 1, right? What happens, as you'll see, I hope on the next slide, is that the acceptances cluster around small values of right? So this is a slide from Radford's paper. This is an evaluation on 16 pairs of normal variables that have unit variance and 0.99 correlation. So it's kind of an odd posterior. What he did show in the end without figures is that for Bayesian neural networks, this wound up being faster than HMC. And I'll say a bit about that later. So this is the standard persistent generalized HMC, which he calls persistent Langevin. Right, and you can see here that the rejections in red are just spread out over the iterations. This is plotting on a vertical axis, it's plotting U, right? And the rejections just happen all over the place. Now with Radford's new scheme, the U carves out this sawtooth pattern. We're basically jittering, kind of moduloing it back into the range. It carves out a sawtooth pattern, and our rejections all cluster around high values of U, and you'll see down here with low values of U, we get sequential sets of acceptances. Now there's a tuning parameter, how closely spaced these sawtooths are. But what this shows is that, well, doing this with this sawtooth pattern is about twice as efficient, right? As he's got bunches of different things carved out here for various deltas and for various settings for how much you preserve momentum. But this is a relatively easy problem. It's really, this is the thing we want to concentrate on, right? Because that's the more realistic evaluation. This is a little toy problem that shows you how the algorithm actually works. So brilliant idea, right? This fixes GHMC to the point where it's actually faster than HMC. Super cool, right? One thing I wanted to talk about, well, I think I love this slide, but I'm going to actually skip it in the context of this talk because we're running low on time. So HMC and Mala, right, and generalized HMC, even the way Radford did it, fail on the funnel, The problem is that by fixing that step size, we can only sample through some interval of this. And you can see this in this plot from my paper with Chirag Modi and Alex Barnett, which I'm going to talk about a little later. You can see over here, these are for different step sizes ranging from 0.5 to 0.01, right? And you can see on these, what these are is a plot of what was accepted and what was rejected. And you can see that we never, ever, ever propose anything that's too small. What happens is these vertical dotted lines wind up being hard cutoffs for how deep into the neck of the funnel we can get before the Hamiltonian diverges. So what happens is our step size is too large for a step size for a first order algorithm to actually deal with the curvature. Right, so we wind up taking a step in the direction of the gradient from here, and we go way outside this colored band and just reject all the time. That's what these are. And depending on the step size, that's what happened. If you make the step size low enough, you can keep going down, but then you start failing being able to sample this or needing like millions of iterations, so we don't have enough time. Right, so what we want to do is fix that problem. Right, so now I'm going to tell you briefly about delayed rejection. This is a technique from Mir and Green in 2001. The basic idea is you do Metropolis, but if you do a single iteration, but you try again if the proposal got rejected. It requires a Hastings adjustment, which is down here on the slide for detailed balance for trying again. So I'm assuming the first level proposal is F1 and the second level proposal is F2. What we're going to do in practice is do HMC updates with smaller step sizes. So what happens if our first proposal gets rejected, we're going to try again with a smaller step size, right? Because the problem is when it gets rejected because the Hamiltonian diverges, we can fix that by moving the step size down. Right, so the first level proposal is going to be S equals F1x. So S is going to be our proposal at the first level. The acceptance at the first level is just our standard density ratios, right? The proposal density over this. If that gets rejected, we're going to go on to a second step. We're going to make a second proposal, Y. And now its acceptance probability is this. We've got Y over X, which is the Metropolis ratio. And this is the reversibility. This is basically the Hastings correction for the probabilities of going backwards. G in this particular case is equal to F1 of V. It's actually a ghost proposal. This isn't one of our proposals. You can keep going on this at nested levels. The next page has a figure for this. So the idea is if we try S, and that gets rejected, then we try F2, our second proposal, and then we try Y. That's going to be accepted with that probability alpha 2. This ghost proposal is what happens if we take our first level step and apply it to Y. Right? Here we do it with the negative gradient. There's a lot of discussion in this Mir and Green paper that actually shows that this actually works. This I just put up here to show you that we can do it for 2 steps of retrying. It just gets more complicated and you can keep going. It's a recursive scheme that's hard to draw up. But the basic idea is if we reject, try again with a smaller step size, do a little fussing around the edges to deal with detailed balance, right? Delayed rejection, HMC, this is what Chirag Modi, Alex Barnett, and I came up with and published last year, right? The key is to try again with reduced step size. Sasha Saul-Dickstein and Campos and Sancerna both tried this in 2014, but instead of starting again where they started from and taking a smaller step size, they started from the rejected proposal. And we know that's not going to work with multiple scale proposals because the thing was probably rejected because of divergence. Right, and we evaluated 3 levels of retries in the paper, and we basically just scale them down. Right, so we take some fraction and we either take the second one to be half the step size or a fifth of the step size, sometimes even like a tenth of the step size. And then for the third, we go a fourth, a ninth, a 25th or whatever. Right, DRHMC, well, here's the evaluation on Neal's funnel. Right, this is a complicated graph. You can see HMC up here, performance. This is on the vertical axis, a log scale sort of cost measure. I'm not going to try to go into details on this. It's basically gradients versus ground truth. The problem is with HMC, it doesn't actually get the right answer. So effective sample size isn't really meaningful here. So this is put there to give it some sense of this is what HMC is doing and how long it took HMC to do its thing, but HMC is really getting the wrong answer, which is taken into account in this diagram because we're measuring. These are various settings of delayed rejection HMC. The point is, these all manage to solve the problem, right? They're not only faster, they actually get rid of the problem of not being able to go down further into the tails, right? So that was great, but the problem with that is we're still doing HMC. We're still taking these long trajectories, and every time we retry, we double the steps in order to maintain the same trajectory time, the same integration time, because that tends to work better. What we did this summer with Gilad Turak, who was an intern working with me and Chirag, was we decided to put delayed rejection and generalized HMC together. The simple way to think about this is we just swap delayed rejection for Neal's non-reversible uniform acceptance, right? This has two benefits. One, it fixes GHMC just like Neal's approach did by imposing a very high acceptance rate. You retry, the retry acceptance rates are very high. And unlike Neal's approach in standard HMC, it works for multiscale distributions, right? The other thing is it actually mixes faster than delayed rejection HMC per gradient, right? And it also mixes faster than HMC, but handles varying scales. So Gilad was an undergrad. He's actually going to come work for us for a year before grad school next year, which is really exciting. And Ed Raldus is working on adaptation for this, which wound up leading to him developing the bridge stand package, which we use all over the place now. Here's the evaluation.
Sorry Bob, can I just interrupt
Please.
quickly because there's a quick question in the Q&A. So someone's asked about the Neal update, the non-reversible uniform acceptance thing, and what's the relation with detailed balance? Does the overall algorithm still satisfy detailed balance, or is there something else going on here?
Yes, yeah. What Radford showed was that update of U still has the right stationary distribution. It still has a uniform 0-1 stationary distribution, and that's what you need to make Metropolis go through, right? So yes, he had the proof that actually maintained detailed balance. Yeah, personally, I do variational inference on the side and throw getting the right answer out, but here we're trying to get the right answer. So yes, all of these methods actually work, at least on the constrained set of problems that they can fit. Like Radford's thing won't work for multiscale distributions, but it works as well as HMC does. In fact, it works better than HMC. Anything else on that?
No.
Okay. Okay, so here's the evaluation. So we have vanilla generalized HMC and HMC, and you can see that both of those sort of fail to get down into the neck of the funnel with the settings we used. And here you have a comparison of generalized HMC and delayed rejection HMC. So this is delayed rejection generalized HMC, and over here it's delayed rejection HMC. The vertical axis is effective sample size per gradient. So what you can see here is that the delayed rejection generalized HMC is better than our original algorithm of delayed rejection HMC. So with delayed rejection, it helps to move to generalized HMC just as it does moving from generalized HMC to this, right? So these numbers are better, higher effective sample sizes by about a factor of 2 than our delayed rejection HMC. So we got here just at the end of the internship, so we were super psyched by this, right? So our delayed rejection generalized HMC outperforms delayed rejection HMC, right? Which is similar to Neal's, but handles multiscale stuff, right? We tried two different things. We tried actually retrying with one step and then retrying to keep the integration time the same. They worked about the same. We haven't written the paper up for this, but the details are forthcoming, and we have a public repo if people are interested in seeing the code. One more thing I want to talk about before we're done in a few minutes, which is some work. So Matt Hoffman rears his beautiful head again and solves yet another problem for us. So you may remember Matt from coming along and solving the problem with HMC that it was impossible to tune. Right, so Matt invented the no U-turn sampler, or NUTS, while we were working with Andrew about 12 years ago, Andrew Gelman, and Matt had a lot of tricks. We called something the Matt trick, and he got offended because he said, I've got a lot of tricks. Here's two more Matt tricks, or maybe they're from Pavel Sountsov. They didn't say who came up with the tricks for this, right? So MEADS is their latest algorithm. There's a paper here I'll give you the citation for later. The starting point is Neal's non-reversible acceptance generalized HMC, right? The nice thing is this is less wasteful than HMC or nuts, right? You could, one thing interesting, Nicolas Chopin just wrote a paper on waste-free sequential Monte Carlo that uses very similar ideas. So HMC doesn't reject a long chain of leapfrog steps, right? So if you look at something like generalized HMC, HMC can be wasteful because we can do 100 leapfrog steps and then like reject them all, right? Which winds up being very wasteful. And compared to nuts, it doesn't have this problem of going forward and backward in time and then choosing a non-final point in the trajectory. We know in nuts, we waste about half the evaluations in terms of squared jump distance just to maintain detailed balance, right? The other thing is it's actually easier to deploy than HMC or nuts using generalized HMC. It's much easier to parallelize because it's not a recursive algorithm, and it's much easier to adaptively tune because the steps are more granular. This is why Matt was interested in this algorithm. So what does MEADS do? It's based on two ideas. One, it uses an ensemble of chains, right? So what we're doing is we're running, so Matt's interested in running 1,000 chains in parallel because they got massive GPUs. Right, so imagine you're in a situation where you're running at least hundreds of parallel chains, or maybe you're just running 16 as in the paper evaluations. What he does is, or what Pavel and Matt do is each group of chains, so this is a group of 4 Markov chains, uses the next set of chains, figures out their curvature and uses that to adapt for the chain you're currently working on. Right, so we can actually precondition with like a diagonal preconditioner doing that. And this is very similar to the Goodman-Weir affine invariant sampler or Ter-Brock's differential evolution. They both rely on this idea of using complementary chains to help estimate the geometry. You can see from this picture that I don't have time to go into the details of that. The second thing he did was came up with a heuristic eigenvalue estimator for the step size. Right, what he did is assume, let's set the, and this is based on some physics reasoning. So he sets the step size to 1/2 times the square root of the maximum eigenvalue of this expected Hessian at this particular place. Right, so H bar is the expectation of the Hessian at the parameters you're at, which is just the expectation of the second derivatives. But we estimate that expectation with an empirical average, right? That's why we have these complementary chains. We can grab those empirical averages and use them on our chain. The beautiful part about this is MEADS is a Markov chain all the way along, unlike nuts, which spends warm-up period, which is not a proper Markov chain, throws everything away and starts again. MEADS is still going to have the burn-in problem, but it doesn't have the warm-up problem that Stan has. It just adapts as it goes along. Right, and this is great with the granular step size because it gives us more fine-grained ways to do that, right? Rather than taking long trajectories, we're getting more adaptation per gradient with this method, right? So that was all I wanted to talk about. I'm sorry, I apologize that I couldn't go into a lot of details for this, but I want to go over the main story again before I end, right? So the idea is that if we add delayed rejection to HMC, we can do multiscale sampling in a way that HMC cannot do by itself. One-step generalized HMC can be tuned to be just as efficient as HMC if you use Neal's trick of a non-reversible acceptance probability. Then delayed rejection turns out to work as well as non-reversible acceptance, and it enables multiscale sampling. This is what we did with Galad over the summer. Then what Matt and Pavel showed is that ensemble methods and eigenvalue step size estimation allow automatic tuning of this. And then what I didn't mention is Ed Raldus, when he was working with this, used the same adaptation and showed that we've got a preliminary version of this working in Julia that works for delayed rejection generalized HMC. So we are optimistic that over the next year, we'll be able to come put a bow tie on this and get this into Stan and probably be the new sampler that we worked with. So here's all the people that were involved. I didn't actually work with Radford and Matt and Pavel on this, but I thought their contributions were so important to this line of thinking that I put them on the second row. And there are the references for the paper. Our paper is still currently in progress. And I hit that. I can't believe I hit that in 45 minutes. It's the first time I gave that talk, so should be plenty of time for questions. So I don't know if you're going to call
yeah.
people, Sam.
Yeah. So Keith, you have a hand up. So do you want to speak?
Yeah. I have a question, I guess. So I guess you've given us a whole bunch of interesting methods. I guess I wanted to get a sense of how many more or less hyperparameters does each one have than standard HMC, and how robust are they in that? Is there an easy heuristic to know which hyperparameters to use, or is it a lot of specific depending on?
Yeah,
on
let me address that in a couple steps. So what Matt did when he developed the no U-turn sampler, so standard HMC has two tuning parameters, the step size and the number of steps. Those turn out to be incredibly sensitive. HMC has this very, very narrow band of acceptable performance, which is step size times number of steps. In fact, this will give me an excuse to go back to the slide that I didn't actually cover, because it talks directly about this. I can find it. Thought I would see it because it has a lot of pictures on it, right? So this is a plot of effective sample size of HMC on a 1,000-dimensional normal, plotted against step size on the x-axis and for 4, 16, and 64 steps. So you can see that once I start going up to this number of steps, that the step size becomes very sensitive. This line right here at 1 is 1 effective draw per sample. What you're seeing is that in certain cases, HMC can get super efficient. This is giving you 10 effective draws per. Yeah, this is giving you 10 effective draws per HMC draw, right? But what happens is the blue is the mean estimates and the red are the variance estimates. So what happens is as the mean estimate gets much more efficient, the variance estimate gets much less efficient, and finding a point that balances those two things appropriately is very hard. The dashed lines, blue and red, are nuts performance on this, which automatically tunes those parameters. So what Matt did is he's like, this is insane. This is a simple problem and we still can't tune it, right? So we have to do automatic adaptation, and the automatic adaptation is that blue and red. And you can see that nuts adapt so that its mean estimates are better than its variance estimates by about an order of magnitude, or almost half an order of magnitude. The bottom panel shows HMC with jittered number of steps. So it's exactly the same setup here, but rather than taking 4 steps, 16 steps, 64 steps, it takes uniform 1-4, uniform 1-16, uniform 1-64 steps. By jittering the number of steps, you break up these harmonics, but you lose efficiency compared to the maximum you could get otherwise, right? So going back to the question we were talking about, HMC is very difficult to tune with its two tuning parameters. This is a relatively easy problem. This winds up in like stochastic volatility problems, giving you like a super narrow band of tuning parameters, right? NUTS actually solved that problem. When we move over into generalized HMC, we replace the number of steps with the amount of refresh. Right. So instead of saying we have a fixed number of steps, we go, instead what we're setting is what's the weighted average balancing between my previous momentum and my current momentum. Right. And at that point, right, so we have the same generalized HMC with the standard setup has exactly the same number of tuning parameters as HMC. When you go to Radford's setup, what happens is he introduces 2 new tuning parameters for U, right, which is sort of how closely together those sawtooths are and how much jitter there is. Those are not super sensitive, and Radford showed how to tune those. The beautiful part is Matt showed how to automatically tune those again. So while with delayed rejection HMC, we have the question of how much do we step down, right, in terms of our tuning parameter. The other parameters are all fixed by MEADS. MEADS actually automatically adjust those. So we're left with 1 extra tuning parameter, which is how much to balance going backwards and forwards, how much to, we're left with the 1 tuning parameter of how much to step down the step size on retries. that winds up not being a super sensitive tuning parameter. The difference between using a step size of 2 and a step, cutting it in half and cutting it in a fifth didn't make a lot of difference. That each of them have advantages. So that's not something Edward's working on tuning that as well.
Okay, thanks.
Right, so we wind up with one extra parameter over HMC, which is how much to step down on retries. But that's the parameter that lets us solve the multi-scale problem. So we're getting something for that. But we certainly don't know as much about automatically tuning this stuff as we do after 10 years of using nuts. So that's why we're not, we're going to roll it out slowly and evaluate.
So we've got a couple of other questions in the Q&A. So let's get on to those. So Mika Kailas asks, what about using the varying step sizes idea within the context of nuts and dynamic HMC? Did you explore that as an alternative to the generalized HMC ideas?
We haven't done that. And the reason we haven't done that is we don't need, like, the thing nuts was trying to solve, which was how many steps to take, is solved by generalized HMC. So as opposed to nuts or dynamic HMC, right, we're just using an alternative method for doing that. So we're solving the same problem differently, right? Nuts set the number of steps. What we need to do is set how much to weighted average the previous thing with the current thing, right? So
I imagine you could still have the same idea though, right? Of you try a nuts trajectory, and if you end up rejecting, you could potentially use a smaller step size, this kind of high level idea, right?
Yeah, it would have been a natural thing to try after we did delayed rejection HMC. Delayed rejection nuts absolutely makes sense, but I think it's being made redundant by the generalized HMC ideas. There's so many other reasons to prefer those over nuts that I think we're not going to be going back. Plus, the person who invented nuts is now using these methods, and Matt knows what he's doing, so that's a strong recommendation.
Okay.
Basically, my advice in life is look at what Matt's doing and try to keep up.
So the next question is from Kieran Gauthier again. He says, Bob, great talk. And now that you're thinking about these delayed rejection HMC, are you not putting as much of a premium now on kind of non-centering models and non-centering parameterizations for hierarchical models, which might actually get rid of these funnels as well?
Yeah, that's interesting. So yes and no, right? I should have had the answer to this because basically I've said this to people standing up drinking coffee, and they always ask me this, right? So the thing is that yes, it's still going to help to non-center, right? Making something that's so what non-centering does is it makes your actual target density much better conditioned and much better behaved, right? It basically makes it much more log concave than it is normally. So the non-centering is still going to crush the centered parameterizations. What this is going to do is it's going to give us a way to actually sample from those centered parameterizations. So it's not going to completely defeat us. And in a lot of cases, those non-centered parameterizations are really difficult. Like if you've got unconstrained parameters and they're just like regression coefficients, it's pretty easy to do the non-centering. It gets a lot harder as you get more complicated models with constrained parameters, for instance, like considered like non-centered hierarchical priors for probabilities, right? If you want to do that, it gets a lot harder for positive constrained values. It's like the code gets more complicated. It gets more complicated to understand. But so sadly, no, it's still there's still going to be room for programmer effort here.
Fair enough. And there's another question from Brian Ward, who says, in the original delayed rejection HMC paper, Chirag also proposed only doing delayed rejection when the original acceptance rate was high or low. How does that work in this case?
Yeah, that's a very good question. Thanks. I didn't, even though Brian works with me, I did not plant this question. So Chirag had a really interesting fix to, well, not a fix, an improvement to basic delayed rejection, which I decided not to, there were so many things in this talk, I decided not to talk about that. That was actually one of the more interesting things in our paper. Chirag's just like, how about try this? And the idea is that you only retry when the probability of rejecting the original proposal was low, right? And again, you need to do a little fix up on detail balance, which doesn't get in the way of other things to make that work. But the idea there is that we want to only step the step size down if we rejected due to a divergence, right? If we had an 80 or 90% chance of acceptance, we don't want to half the step size and do twice the amount of work. We just want to try again, right? So what Chirag did is figured out how to actually do that, right? Using an improved delayed rejection with this. We kind of buried it in the original paper, and the reviewers are like, hey, this is like super important. You should stress this more. So there's also that, which was a cool idea from Chirag. Now, to answer Brian's question, doesn't work so well in this case, right? The reason that we can't do that in this case is we need to keep our acceptance rate high, right? So we don't ever want to reject, even if we had a 95% probability of accepting and we rejected, right? We want to try again. What this might say, though, that just occurred to me now is, if the probability was high of accepting, maybe when we retry, we don't want to step the step size down so much. That's a little complicated for me to answer off the top of my head, but we might be able to make that work.
So some sort of dynamic decision for what the next step size should be based on that kind of information.
Right. I think that would be the way to have the best of both worlds. I don't know if it can be made to work, though.
Sure.
Probably stop sharing my screen here so we can.
There's no more Q&A questions at the moment, but let's give it a couple more minutes to see if any more trickle in, because I have a couple myself. So one of the things that I thought when you started talking about generalized HMC, you made a kind of aside about how sometimes you do things that are approximate. You don't always do things, things like variational inference, which kind of connected me to some colleagues in the more kind of applied math statistical physics world that also use Hamiltonian Monte Carlo type algorithms. And in that community, there's a community that I'm familiar with in applied math, where they typically do use kind of generalized HMC, which they might also call things like underdamped Langevin, where you have this kind of memory. And in order to get around the issues of the sort of the rejections making you change direction, they just got rid of the acceptance rate, right? And they do this kind of approximate, which works for that purpose. But then, of course, you introduce approximation error. And I was just curious, in the statistical community, we've typically not taken that approach. Have you ever considered that kind of approach for Stan? And what are your general thoughts on it?
My understanding from talking, there's a few molecular dynamics people floating around Flatiron who do this kind of stuff. And my understanding from them is that to make their solvers work, they already have such a small step size that their rejection probability is so low that they're not actually introducing a lot of bias into the problem from doing this. They're like 99.9% acceptance probability, right? And they're taking very small steps, and they're doing just gazillions of steps to do these simulations. They're like burning our compute cluster down doing molecular dynamics. It's really a close run thing between molecular dynamics, PDEs for quantum mechanics, and neural networks as to what's eating up all our computation.
Fair enough. So we've got a couple more questions come in now. So Mike Lawrence asks, have you explored the performance of this new approach on multimodal posteriors?
No, right? And really, we don't expect this to work on multimodal posteriors. We don't really expect anything to work on combinatorially multimodal posteriors, like neural networks or clustering algorithms or like LDA or something like this. It shouldn't be any worse than other things. So if you can actually, the energy gap isn't too bad to jump between modes, this shouldn't work any worse. but it's not going to solve the problem. Like just having an ensemble of things, maybe some of them land in some modes, some of them land in other modes, that's actually going to be really problematic because it's going to trash the adaptation. The adaptation in one mode is not what you want to use for another mode, and smearing them all together is also not what you want to use. So it introduces all kinds of problems for adaptation if you do that. And there's no mechanism like simulated tempering kind of thing that would let you move between those and actually get the right balance among the different modes. So no, I don't know how to do that. There's some, I can advertise some work by one of my former colleagues, Mary Lou Gabriel, who since moved from a postdoc at Flatiron and NYU to a faculty position at the Polytechnic. She has a really cool technique that combines using Langevin. So she's one of these molecular dynamics people, and she's working with like Eric Jan van der Linden and a lot of sort of well-known molecular dynamics people. And what she's doing to deal with this multimodal problem is throwing down a whole bunch of samplers, right? Basically Langevin or generalized HMC type samplers, knowing that in these problems tend to have limited multimodality. They tend to come from different configurations of biomolecules or something, at least in the thing we're working at. So they'll have like 4 or 5 modes. They won't have, you know, combinatorially many modes and dimensionality. Then what she does is she takes all these things which are sampling from the local modes and builds a variational approximation to the posterior out of those modes, then uses that variational approximation as a proposal for Metropolis, right? It's brilliant, it actually works, it gets the balance right. The only assumption really is that you need to be able to find all the modes and sample around all the modes independently. Right? So it only works for limited multimodality where you have a clue as to where the modes might be. So it's not a general solution, but it works for these molecular dynamics problems.
And there's, thanks very much. So there's one more question from Kure Kim. And they're asking, could you share some details about the low rank preconditioning that you mentioned in the beginning? Is it related to the reparameterization paper by Matt Hoffman that came out a while ago, or is this a different idea?
Yeah, I'm not sure. Matt writes a lot of papers. I assume this is talking about the neutralizing bad geometry paper that used normalizing flows to condition. I was very sad by that. I went out to visit Matt in California at Google, and I'm like, I want to know how this works so I can answer, so I can build this in Stan. And they're like, that worked by graduate student assent. We can't get it to work for other problems. Don't bother. So we kind of tossed that out. But the idea of doing something like what I was talking about, if you're familiar with the LBFGS optimization algorithm, it's a quasi-Newton method. And what it does is as it's going along the optimization trajectory, it uses the last, say, half a dozen or dozen points you visited. It takes the gradients at those points and uses those to create a low rank approximation to the Hessian, and then it adds a diagonal, so it's full rank. We've used this in our variational inference algorithms to do low rank plus diagonal multivariate normal approximations. And the nice thing about that is if we're at rank J and we have n-dimensional matrices, all the linear algebra operations become nj squared instead of n cubed. Right, so it makes all of this stuff tractable. There's no reason, I think, why you couldn't do something similar inside of Riemannian Hamiltonian Monte Carlo. Instead of using a dense representation of the covariance matrix, which is the thing that's hard to scale because it's cubic and you have to auto-diff through it and you have to condition it, you have to eigen-decompose it and recondition it to do Riemannian to put it back together. That's really, really problematic, right? Doing all of that. So we'd rather not have to think about all of this.
So he's just written just a clarification that he was talking about the automatic reparameterization of probabilistic programs paper, but I think it's probably beside the point because I think you probably answered the main question.
Yeah, that automatic reparameterization was more like, can we figure out the funnels and things like that automatically, I think, if I'm recalling correctly, which other people have been working on. So yeah.
Keith, did you have a question?
Yeah, I have a quick comment and a question as well. So my quick comment is, if anyone is interested in Marie-Lou Gabrier's talk from last session in the webinar, feel free to email me and I can send you a video of that. She gave a great talk on some of the work that Bob is mentioning. And then my quick question is, how well does, I guess, GHMC plus delayed rejection scale with dimensionality compared to HMC? How many more is it similar or with more parameters?
Pretty much identical.
Okay.
Right. You get the scaling for dimensionality from HMC comes from being able to make directed motion without falling out of the high probability mass volume. Right. So the way the gradient field works from the potential that we set up and the way the momentum gets set up in HMC, you can do really long trajectories and still have a very high probability of acceptance, right? That's where the sort of scalability with dimension is coming. The problem is when you take little steps like in Metropolis, you wind up with this diffusive process, which doesn't scale in dimension, right? So it turns out it's pretty much identical. Generalized HMC has the same kind of scaling properties. It's going to come from being able to make that directed movement. Right, that is GHMC with delayed rejection. GHMC has the problem, and the reason it doesn't scale is because it does these reversals and can't make directed movement.
So we've got a couple more questions in the Q&A, but I should maybe just check with Keith first. Are we okay for time, Keith? Do we have a particular time we need to finish this?
So hard stop is 12:30. Did you have a little code demo at all, Bob?
Did I have a code demo? No.
No. Okay. So yeah, we have hard stop at 12:30, so we have a bit of time. If you both have,
I've been around enough. I'm never doing demos live for nothing like this. That's insanity. That is so dangerous.
Yeah.
Fair enough.
Yeah, so we can get through the
I wouldn't even
questions.
want to have to recompile the LaTeX for this live.
I've seen many people do that with bad results.
I know. I've been around long enough. I've learned all my lessons. So
yeah. So Brian Parbu asks, and this I think there's a couple of questions on this theme. Brian's asking, is there going to be a general shift here where Stan will head in the direction of MEADS versus nuts? And this kind of relates to something I was interested in as well, which would be that if that is the case, what's the kind of next steps from now? What are you going to do next to sort of think about how that transition might happen if it does?
Yeah. Well, there's a couple different things. Mechanically, we have a developer process inside of Stan that's going to demand a lot more evaluation than we've already done on this, right, before it happens. So we've got to get the automatic adaptation done and tested on, 100 different models before we're willing to roll this out. We can roll it out experimentally, and we'll roll out algorithms that'll work with Stan through BaseKit, this Python package that we're developing that works for any kind of Python defined densities and gradient functions. For getting it to roll out in Stan, it's unlikely that this is going to happen like in the next year, right? Our project's slow enough, and this is like changing the very core of it that no one's going to be happy with this. And just given the cycles that everybody has working on it, I don't expect this to land sooner than middle of next year.
But that is a potential.
That's what we're
scenario.
thinking.
Okay.
Yeah, this is just a corollary of look at what Matt's doing and do that.
Okay.
That's worked for me my whole career in Bayesian inference, which is only the last like 10 or 15 years. But
so Mika Kailas has another question, and it's about MEADS for adapting generalized HMC. And he's asking about whether there's some kind of level of approximation unless you have a kind of the number of chains in the adaptation tends to infinity.
It turns out that you can show that this actually obeys detailed balance. This is kind of a standard technique. An easier version of it is the Goodman and Weir affine invariant sampler, which is a cool like adaptive Metropolis sampler. It's worth checking out if people haven't seen it. And that has the proofs, and Matt and Pavel go over basically why this will work. But basically what you can do is you can take the complementary chains and use those to adapt your chain without disrupting the fact that the whole ensemble together evolves as a Markov chain. right? So the point is that the whole thing is evolving as a big Markov chain.
And I guess a kind of more
Do you have voice
practical
now?
follow-on. Oh, sorry. Yes,
Oh,
Mika's on the
sorry.
line. Yeah,
Just saying. So this is it's not something I came up with myself. It's I was talking to my supervisor, who's an, at least Sam knows him. He's pretty good with his adaptive methods, and his comment was that there's a subtle mistake, at least in the MEADS paper argument, for this adaptation. Being satisfying a detailed balance, namely the assumption there is that the chains, the joint PDF of the chains factorizes so that the chains are independent, and that's the assumption, and then you show that the marginal of the single chain has the correct distribution.
Right. Okay.
But you should also show that the chains are independent after its first step in order to repeat this, in order to get the. It's a bit of a technical thing to explain now without the formulas here, but at least I was convinced that the argument in the MEADS paper and what was the other paper I looked at? One of these ensemble complementary adaptation papers makes the same rather subtle mistake there. That it's not actually satisfying this, but I suppose this could be a longer discussion.
Yeah, if you have an example of this written up, I would love to see it and think about this more. This is going to be more than I'm going to be able to work through mentally here. But I would love to I would love to actually get to the bottom of this and understand whether this is giving us some kind of approximation error or not.
Right. Yeah, I haven't implemented the algorithm myself. I was thinking of trying to do that at some point to see if I can actually show that it has bias or not. But at least the argument, I don't see how to make the argument correct. But
yeah, and it may be the case that yes, it has bias that is based on the number of chains that goes to 0 with infinitely many chains. And Matt may just not be worrying about that because he's normally working in like 1,000 chain situation. So it may be something that would be like
right. Then I'd imagine that the
more problematic
dependence will vanish anyway. So yeah.
Yeah, but interesting question. I had just sort of taken it on faith that this was going to work because a lot of good people had gone through the proofs and they seemed sensible to me. But I will dive in and look again. So thanks for bringing that up.
I guess a kind of perhaps a more practical follow-up would be how many chains had you been using in your experiments in this kind of when you're evaluating this method? Are you talking about thousands of chains? Are you talking more about tens or?
I think Edward's been working on like the order of 100.
Okay. Chains. And do you imagine that that would be what we do at Stan or?
Yeah, it's sort of an interesting question about where computing is going. Right. One of the reasons Matt's doing this is, computers are not getting a lot faster on single processors year over year. Like I kind of miss the 1980s where every 18 months your computer, you bought a new computer and everything went twice as fast. That doesn't really happen so much anymore. And the question is, how are we going to scale with computation? And I think we have to do more parallelism. And one of the things Matt's been working on with a whole bunch of people, including Charles Margosian, who's at Flatiron and was a student with Andrew Gelman, is working on a regime where you run massive numbers of chains, like 1,000, just to the point where you can get one draw from each of them, right? And then you put one draw from each of 1,000 chains together. This is very compatible with modern hardware. Like this is something that's like easy to run on our clusters. It's easy to run on Google's clusters. So it's an easy way to scale things up. And the question is, are we with Stan or should we focus on running on somebody's desktop or notebook? Or should we be rethinking that the future is going to be everyone's going to be running on a cluster? Right. I wander around Flatiron and we are the only people who run our stuff locally for the most part. Everybody else is running everything on the cluster because the computing's so intense. And most of our customers, if you will, for Stan are like fitting models on their notebooks, right? So it really is a practical question of whether we're going to be able to do this automatic adaptation with few enough chains to get it to run in people's notebooks. If not, right, if it turns out to be really problematic to do this with a few chains and running more chains isn't practical, then we're going to either have to do something different for adaptation, or we're going to have recommendations that say in this situation use this sampler, and this, you know, this hardware or whatever situation do this, and in this hardware situation do that. Right, which is ugly but inevitable if you are in that situation.
Sure, fair enough. So there are no more questions in the Q&A at the moment, and I think we've had a pretty good discussion at this point, so it does feel like quite a good time to wrap up. Is that all right with you, Keith? Shall I just summarize quickly? Okay.
Yeah,
perfect.
this is great.
Yeah, so I just want to take the moment to say thank you so much to Bob for a really interesting and inspiring talk. I particularly really enjoyed the fact that you really told the story of how lots of different ideas from different people combined in order to, and if you combine them in just the right way, you can end up making something work, because in my experience, this is actually how the majority of research projects go. But then you write the paper in a way that it sort of looks like you sort of came up with everything. But so I really enjoyed you sort of telling a much more realistic and honest story of how the real research process goes, and how you write the first paper, and then you sort of, it's okay, it's quite good, but then you still sort of want to make it better. And then you sort of manage to do that. And I always find online seminars very strange that you don't get the clap at the end of the talk, but I'm sure that everyone's giving you a very loud clap in their own homes at the moment. So thanks very much, Bob, for a great talk.
Yeah, you're welcome. This is fun. I like the format of 45-minute talks and half an hour a question. I think I'm going to adopt this.
Yeah. So thank you so much for joining. Thanks so much for joining us, and thank you, Sam, for spending your evening with us as well. This was a great talk. Just as a heads up, for next week, we have Yang Yang, and they'll be talking about, one second. Just want to get the title right. And Yang Yang will be talking about generative adversarial symmetry discovery. So that's going to be a very interesting talk there on finding geometric symmetries using machine learning. So thank you, everyone, and hopefully see you next week.
Bye.